Okay, it looks like most people are connected. My sound is okay?
Yeah.
All right, awesome. So yeah, maybe a few people have tried to writing to me. Yeah, since Friday, I haven't had time 1 second to check my email, but I plan doing that very soon. So sorry about that. Otherwise, yeah, so homework number 1, it's coming soon. If you're having trouble, please ask me questions, and mostly come to office hours. So I just had one, otherwise I'm going to have another one on Thursday, but so that is going to be in my office, because yes, this is the last class in which we are not in person. So at last I'm going to see you, or at least see your eyes. So I'm looking forward to that. Just so that sometimes I may see confused eyes and I know I should spend more time. Otherwise, I'm happy with what's going on. All right. So without further ado, well, are there any questions, issues about the class or anything? Yeah, tutorials are in person too. So yeah, I think this is great, because it's good to have personal interaction during tutorials to really get the message through. Okay, so let's start with today's class, linear models. So this is yeah, the meat of the first part of this class. So it's like up to now we've checked and dabbled in some stuff that's more fundamental, high level, but yeah, this is a real big chunk of the matter. So linear algebra, I'm guessing most of you may have seen at least some of it in no, maybe not most of you. So just briefly, can you see in the chat whether it rings a bell to you or not? So those who have seen it already. Yes, yes. Or, yeah, all right. Yeah, ages ago. Yeah, so yeah, it's going to be a refresher. So one thing is we are not interested in all the geometric stuff. So well, it's still interesting and it's still super close to that, but finding the intersection between yeah, a hypersphere and a plane or a vector or whatever, this is the stuff you might have seen earlier, because the elementary linear algebra, you don't really know if you're using that to go in physics or in computer graphics or in econometrics or statistics or in anything. So the linear algebra we're going to see today is what's useful for mostly for economics, I would say. And of course, yeah, econometrics later on. All right, so this is a fundamental topic, something that's being actively researched in applied math by so many people, and as well in computer science as in pure math. So yeah, solving linear systems or non-linear systems for that matter, that's really important. Of course, we're going to stick to simple things, but know that this is a huge topic. Something that's super interesting for myself, but that still I find that I struggle a lot. So if you find it hard, it's normal. So we're always learning, we're always understanding new stuff. So please stop me, say it's going too fast or whatever. I'm here to help. All right, so linear algebra. So that's So I would just say as what I've been saying, it's a central topic, central subject to almost all area of mathematics. So in particular, matrix algebra. So why would we care about matrix algebra? Because what we've seen so far is, oh, let's look at a simple system of two linear equations and two unknowns, or a more complicated three linear equations, three unknown. But what about four? What about five? You could spend a whole bunch of effort trying to solve a 4x4, 5x5, 6x6, 100 by 100, 1,000 by 1,000, but at some point it becomes extremely hard, and you don't do that by hand. So you do that using computers. So before, like in the first half of the 20th century, maybe. So if you were in grad school, then you could seek employment in the summer, working for professors who needed to estimate stuff, because you didn't have computers. So the professors would just hire a bunch of students and say, please invert this matrix this summer. So you had a big matrix, and then everybody, what they would be doing is computing and checking computation, computing and checking computation all day long. And then maybe at the end of the summer, you would have a result. So that was painstaking and slow. So be glad that we are not back then. But yeah, so what do we do with the matrix algebra? So we solve large system of equations with computers. So and in a systematic way, so in a compact way, we try to write as few things as possible and to synthesize all the information. So so we and then we can test what we want to test. So systems have solutions, or if they have 0, 1, or an infinity. In a more direct and easy way. And yeah, provide many tools. To quickly solve systems. And so for very large systems, we have approximations. Numerical approximations. That can be very efficient, very quick. So one very popular is the conjugate gradient method. We're not going to see this. This is really a computational topic. But for this class, we're going to have exact solutions for small systems. So systems that you're going to have to solve. So a question that you may have is, so we've seen that we may have linear system of equations for economic models, but what about non-linear models? So because of course, what we're modeling here is a bunch of equations that represent an economic model. And then we want to find solutions to them. So a question, the legitimate question is, what if the system is nonlinear? What if it cannot be represented by a system of linear equations? So a bunch of questions a bunch of things I may say is, so often, what we're interested in is whatever happens close to the equilibrium. Yeah, and here I have represented briefly what I meant, so I'm just going to paste it. All right. So imagine that you have a supply and demand, or rather demand and supply, and you have no clue if it's linear or not. Well, the thing is, you have no clue at all what happens outside the equilibrium, because everything that we do observe in real life happens around here. If it's say $10 and 1,000 units, then you never really see like 30 or 0 or $1. All we have at our disposal to estimate these things are what happens when there is, say, a small disturbance in the market that brings costs higher or brings demand lower or stuff like that. And this is how we're able to sort of estimate the demand and supply, but just around here. Here it's uncharted territory, and frankly, it's not that interesting. When we do draw these curves for you, or these lines, then we draw them all the way to show you that they, in principle, they can exist, but in practice, we never know. From a scientific perspective, at least, we have no clue. We have no way of knowing that. And that doesn't matter, because all what we want is elasticities, and so as such, all what we really care about is the derivative. So we care about what's happening very closely. And if for some reason we want to know what happens a bit further, then it's almost linear. And so yeah. So one other thing that we can do is, if it is close to the equilibrium, but nonlinear, we may use approximations. Such as Taylor's theorem. So this is used a lot in so many places in science. It's used in math. It's used in statistics a lot, in econometrics a lot. So it's a way to get rid of a complicated function and just express it as a series of polynomial, or just as a big polynomial, and it helps a lot. And one other way to deal with nonlinear function is the following. So if we believe that a model is really nonlinear, so if we really have good reason to believe that it's sort of silly to try to represent it with a linear function when we know for a fact it should be nonlinear. So then what we can is convert it to a linear system. So for instance, if I have something like y equals to ax to the b, so I really think that this is a nonlinear relation where b is 2 or 3 or 4, for instance, and x is a variable, y is a variable. Then what can I do? Well, I can just take logs on both sides. So rather than use y by itself, I'm going to use log of y, and I'm going to use log of x. So I'm just going to get log of v plus b log of x. So here I started from something that's unwieldy and difficult to solve, and here I have something that's very easy to solve. Doesn't always work, so there are exceptions. Yeah, so that's that. Okay, I'm not going to go into that, but basically, if you have in your data you have too many zeros here for the y variable, it might be almost impossible to estimate. But if you have nice values for y and x and non-zero values everywhere, then you should be good. Yeah. All right. So this is the motivation for this chapter, and for what we're going to see the chapter 4, which is quite a substantive chapter. All right. So this is the motivation. Now let's go into many definitions and notations. Yeah, that's what we have to do. So I'm going to be a bit optimistic and just say some notation, not too much. All right. And of course, these notations are not absolute. If you open a mathematics textbook, they use their own set of notations. If you use an economics textbook, they have math, but they have the sort of notations that economists like to use. So it's not always the same. Here, I'm going to stick with what they show in the book and what you're most likely to encounter later if you have econometrics classes, for instance. Okay, so let's revisit the two market partial equilibrium examples. So what we can do is write all the, so if you remember, you had two sets of demand and supply. And what we did is find the equilibrium for each market by setting the supply equal to demand. But then we still have left two equations with prices and yeah, the prices are gone, but still two equations. Two equations with prices, but without quantities, but we still have to estimate them. So the way we would write them in a very general way would be something like this. So C1 plus C2 P2 equals yeah, should I do that? Yeah, all right, that's useful. I can do that. Equals minus C0. This is just because I had plus C0 here equals 0, but I can just write it this way. So yeah, let me do everything step by step. Equals 0, and then say I have gamma 1 plus gamma 0 plus gamma 1 plus gamma 2 P2 equals 0. So that's why. So after solving for using the market equilibrium, this is what I get: two equations that are both functions of each of prices. And I could ask you, oh, please find what the equilibrium prices P1 and P2 are. Or is it possible to find such equilibrium, or do you have no equilibrium or infinite number of solutions? And here, what we're going to discover is ways to do that systematically. So just to illustrate what we're doing, I'm rewriting these, putting the constant term. These are constants on this side. So this is going to be equal to minus gamma. Yeah, and anytime you see some letter you don't know, assume it's a Greek letter. So here it's our friend, the Greek letter gamma. That's quite popular, I would say. So the key to be popular for a Greek letter is to be easy to draw and to not be too confusing with some Latin letters. So for instance, in Latin letters, we have I, and then in Greek letters, we have iota like this. So I'm telling you, you're not really going to see iota a lot. Yeah, lambda is nice too. Pi, theta is nice. Pi is nice. If you really hate your readers, use zeta or xi. And I'm telling you, if ever I write something on the board, I'm never going to use zeta. That's impossible to draw it. Yeah. Yeah. What's how do I psi? I don't remember. Yeah, that one. Yeah, psi is nice. Yeah. All right. So these are Greek letters. After a while, you'll learn all of them. I assure you, and then you can travel to Greece. All right. So here is so this we know that for up to now. So this is a system of two equations and two unknown. And then what we are going to do is rewrite it with vectors and matrices. So the way you do this is you write it this way. yeah, profit or pi. And we write it this way. So, so this, I'm going to create a matrix here times a vector. And then I'm going to explain to you everything that's going on. So equal a vector. So here I'm going to, you see that I have two things that are repeated. P1 and P2 appears in both equations. So this means that it's sort of, that's redundant. So I don't want to show many times the same equation. I know that the same variables, I know that there are the two variables that interest me. So here's what I'm going to do is I'm going to put the two variables here. So P1 and P2. And here I'm going to have C1, C2, gamma 1, gamma 2. And here I'm going to have a vector with my constant terms. So minus C0 and minus gamma 0. All right. So this is exactly the same. It represents the same set of equations, but this is a matrix. This is a vector, a column vector, and this is a column vector too. All right, where? So let me be more precise. So yeah, oh, and by the way, I can, so what's neat about this is I can rewrite this in a more compact form. I know this is an object, this is an object, and this is an object. And you usually represent it very simply as A, P equals C, for instance, where A is this, P is this, and C is this. And as soon as you see this, then you know that what you have is a matrix with a certain number of rows and columns, a vector with a certain number of rows, and another vector with a certain number of rows. If it's just one, then AP equals C could be perfectly equal to C1, P1 equals minus C0. But then it can be that you have many variables and many equations too.
Sir, will the annotation always be AP equals C?
No. I chose the notation I gave you.
Okay.
Well, here I chose P because it's P1, P2, so it sort of makes sense. And here you chose C because it's sort of the constant terms, so it's what is not a coefficient of a variable. And here I just chose A because well, I could choose any other. Sometimes you.
Okay.
Yeah, sometimes you may say, yeah, sometimes we have something like AX equals Y or BX equals Y, or yeah, it depends. AX equals B sometimes.
Okay. Also, the C and the Y, the Greek Y,
Hmm.
what do they stand for? You just chose them like that?
Yeah, the gamma there. Yeah, it's just this is just to differentiate between two. It's because before yeah, it's I went into a bit more effort into solving so this is part of the big system of like two demands, two supplies, and two prices that I showed previously. But yeah, it could be anything. It could be numbers. These are numbers, so there's no real reason why I chose them. So one thing I'm going to enjoy doing mostly is to use say something like letters and numbers, or numbers and letters, so that you can know that there are certain rows and certain columns. So yeah, it's coming up later. But yeah, so it's not unique. So by any means, the notation may change. One thing I already can say about my notation, though, to not confuse you, is I'm always going to represent column vectors and matrices with brackets like this. Okay. In some textbooks or some other contexts, sometimes people may use this for matrix. Which is fine, but I don't want to confuse you. So this is a matrix all the time. So if I somehow don't do that, please tell me, no, this is a matrix, it has to be brackets. But yeah, very good to ask this type of questions now. So A is this. So we say it is a. This is a column vector. This is a column vector. It's a vector, but with elements stacked on top of each other. So we say it's a 2 by 2 matrix of coefficients. And note that here, this is not the same times as we were using earlier. It has nothing to do with sets. This is just to say that it's 1 dimension by 2 dimension, but it's sort of equals it in the following way, is because I'm really going to have row 1, row 2, column 1, column 2. So I'm going to have elements 1, 1, 2, 1, 1, 2, and 2, 2. So in a sense, it's yeah, it's like a Cartesian product, but it's a bit different. P and C. P is a column vector and C is a column vector. Yes, P is P1, P2 is a 2 element vector. I shouldn't even say row vector, column vector, so of unknown And I have that C is C0 gamma 0. Yeah, this might not have been the best because I have C there, C0 and gamma 0, but yeah, sorry about that. Is a two-element column vector of constants. So don't worry, I'm not going to ask you at the exam what is a column vector or what is a. It's really for you to know what when I'm talking to you, what I'm saying. So, but sometimes I'm just going to say it's a vector when it's unambiguous. But yeah, so really technically it's just that it's stacked on top of each other, so it's a column vector. But so I'm going to say that more commonly. So this is for a 2x2. So in general, we could have n by n. So that this is what is interesting about this is now we can go up to as many elements as we like. So we can have a n by n, yeah, a system of n equations and unknown as so you would have, for instance, A11 x1 plus A12 x2. So here it's not A12. If there is confusion, I may write it with a comma there. But since this is clear that what I'm saying is it's first and then second. So yeah, I'm going to just write it this way. And press A1 n xn equal to D1. So you see here, I sort of changed my notation a bit. And then, so this is the first equation. Then the second equation, I just have a second set of coefficients. And I would have D2. And then down the row, I have N1, N2, and Dn. Here I have, can I find my dot? I think it's here or not. Yeah, here. All right, so this is how I would write it, but you see it's tedious. So a better way would be to write it as a large equation. So just to see where, or Aij. So here I is a variable and j is a variable. This is the coefficient of the ith equation of the jth variable. So then how I would write this? So I would have my equations here, A1, A2, and multiplied by my variables x1, x2, xn equals to E1 to En. Yeah, let me do a thorough job.
Sir,
Yeah.
I have a small question because I didn't take linear algebra. The x2, wouldn't that be multiplying it? Okay, so they all get multiplied by the vectors on the right.
Yeah, so this equation gets multiplied by this vector. So we are going to see more in detail how you manage matrix vector multiplication, vector matrix multiplication, or matrix matrix, or vector vector. But yeah, this is where we're going. So you see that how do I get back this equation? Well, I multiply first element here, A11 with x1, plus second element with the second here. I get this, plus the third element with the third, and up to the nth element with the nth, and I get this thing here. This is how I get back to my system. So,
okay, perfect.
Yeah, and we're getting there. Don't worry, I'm going to show you how we multiply stuff.
Also, what would happen if the vector was shorter, we could say, than the matrix?
If you have a n by m, for instance, so you don't
if it
have
was
this
x n minus 1.
Okay, so if I had this, for instance, this would be n minus 1. Yeah, can't work. Good, very good. So what can you be more precise with can't work?
Okay, so they have to match, the vectors and the matrices have to match.
I haven't said anything. There is no, I'm not going to be arrested by the police if I write it this way. But something may go wrong. So what's wrong with this? That's a question for the whole group. Think about what's going on. It's not an easy question, but it's where we're going. So I'm just going to, there are constants will not correspond. Here I have, yeah, I have to think, yeah, I haven't thought it myself. What's going on here? I have n variables and n minus 1 equations. So, oh yeah, no, it's, yeah, it's absolutely true. I cannot have this. Oh, yeah. So here, yeah, here, that's for sure. I have to have, this has to go to n, yeah. Otherwise, I cannot multiply. Yeah, okay. Sorry for, so this cannot work because I have to have the same number of elements in the first row as I have in this column vector. Because what I want is clear correspondence. Otherwise, yeah, this dimension doesn't make sense. Okay, yeah. So, but imagine I have this though. I have yeah, I have n variables, but n minus 1 equations. Yeah, thank you, Bero, for putting an end to my shameness of trying to do a matrix multiplication that doesn't work. So somebody can think of what's going to happen if I have this as a system. Yeah, if it's, so I will tell you in personally, in my papers, sometimes I put a comma, sometimes I don't. So it depends on the context. Yes, one variable is left hanging. Okay, so I'm going to tell you how you think about these things. So here I'm writing something that's extremely abstract. So what is it? You don't even know how many equations you have, how many variables. It just looks so general. How can you think about it? Well, mathematicians are always start with something maybe very weird or abstract, and then to make sense of it, the first thing you have to do is imagine, oh, how can I simplify it as much as possible to create some example I understand. So let's simplify this. So imagine n is the simplest thing I can imagine. So n is 2, because I'm going to get n minus 1, which will be 1. So in that case, I have a1, a11, a12, x11, x12. So I have how many rows here? I have a single row, because it goes from 1 to n minus 1, which is 1. So from 1 to 1. So I have just this. A11, A12, x2 equals d1. So what do I have? Well, it's perfectly fine. It's just that I don't have a unique solution. I have 2 variables that I'm trying to find, x1 and x2, but I have a single equation. So what do I have? I have a straight line. I have an infinite number of pairs of x1, x2 that gives me a solution. And if I went into higher order, I could find the same thing. If I have 2 equations, but 3 variables, then again, I don't have a solution. So it's, yeah, what Navtej said is exactly that. It's one variable is left hanging in the sense that one variable is free. Here, if I set a value for x1, then I can have whatever value I want for x2. I don't have a unique solution. Yeah. So this is why we write it this way. So we want n equations and n unknowns. But so this is to give us a chance to find a unique solution for our system. So I'm just going to write a comment there. So we need as many equations as unknowns if we hope find a single solution to the system of linear equation. Still possible we don't have one, but at least we need as many equations as unknown. And by the way, just taking the first one, so saying, imagine that it goes to n minus 1 and say, oh, I'm just going to complete the square by adding the same one twice. Well, that doesn't work, because this is exactly what we've seen last class. If you just copy the before last equation to the last equation, then what do you get? You get 2 lines that are confounded with each other. So it doesn't help you find a unique solution. So this is why we say that even if we have the same number of equations as unknown, still it's possible we don't have a solution, because some of them may be sort of redundant considering the others. So I'm all going to put more flesh on this concept. This is where we're going. All right. But still not sure. Okay, where was I? Yeah. Yeah, so this can be rewritten easily as just x equals d. So I think in the book they write it this way. So sometimes they write b here. So let's get yeah, where so A is this, X is this, and D is this. All right. And one super useful notation that I have found because later on maybe I'm going to do it, but probably not. But yeah, I still have the hope of proving a bunch of the properties we're going to show for matrices, and a super useful way to express the matrix A. So the matrix A may be written compactly, as A is just, oops, brackets, AIG, and then I say ING equals 1, 2, n. So what I'm saying is I have a square made of elements aij, where each element I and j go from 1 to n. So I'm going to have this. And it turns out that if you write it this way, it makes proving things with it super, super easy. But yeah, I still don't want to bang on it because it's maybe it's too abstract. Yeah, so of course, where I indexes the row and j the column. Oh yeah, and note, when expressing the dimension of a matrix, we always start with the row, then column. So this is a convention that everybody agrees with. So when you say element A21, you know it's second row and first column, all right? So 1 is second row, first column. So this you just have to learn it to learn to it's a really big amount of stuff to learn. That's life. All right. General definitions. So right. No, sorry. A scalar is some number. Example, x equals 2. So here, that's just yeah, that's just a number. It can be mostly it's going to be a real number. So yeah, so one of the greatest mathematicians of the 20th century, maybe the greatest, did work that was so abstract that so anytime we solve things for linear systems in the reals. So we imagine that here all these things are real numbers. Well, he showed properties for any number systems. So for for rational numbers, for numbers that were just modulus of some other numbers, for anything. So yeah, it can be extremely abstract and you can still understand the properties of these things. But for us, these are usually in the real numbers. And then a column vector. Here it's going to be a matrix with a single column. So you can write it yeah, so you would write it this way. So for instance, V equals V1, V2, V3. A row vector is a matrix with a single row. So you would write, for instance, and a way you could write it is V prime. So this is the same as V, but this operation transpose shifts all the rows into columns and all the columns into rows. So then you would get the following. So you would write V1, V2, V3. So this is a way that we oftentimes represent things. You may not say, you may say it's something new, like I don't know, G, for instance, or whatever, but it's since we usually represent things in a column fashion. So if you say something like it's V prime equals this, then you sort of know that this is there's a underlying, there's a column vector that looks like this. Then all you have to do is shift these things vertically and you get it. But I'm going to go back to this transpose operation. Don't worry about it. All right. So M by N matrix A is an array with, so an array is just a square of numbers or square of anything for that matter, but with M rows and N columns. We may write it A by N this way. So that's a way to express the fact that this is a matrix with M rows and N columns. All right. Sometimes, so you see that here I didn't write, I just said it's A. Sometimes if I don't want to specify the dimensions, I don't need to, because many things you can just say that it works whatever the dimensions are, or you assume that you have the right dimensions. And by the way, when I just got rid of all the this row, that was wrong, because this has to have the same number of columns as the matrix there. Yeah, but so if I want to express the dimensions of A, I can write it this way. And yeah, I'm going to oftentimes do that just so that it's clear for you. And by the way, so a square matrix, can you guess what it is? It has the same number rows and columns. Right. All right, so yeah, this is basically it. Do I need to add other things? Oh, I'm quite good actually. Okay, matrix operation. Because of course, what we care about is what can we do with these things. Yeah, so I don't know today how much I can fill your TA session of Friday. I'm going to see, because it's so filled with definitions that yeah, at some point if we don't get to whatever you can do with it, then all right. So equal matrices. A equals B. If yeah, write it this way. If and only if Aij equals Bij. So what does that mean? If IFF means if and only if. So it means that A IFF B means if A then B, and if B then A. So it means it goes into in both directions. So you might know that or might not know that. That's all right. You're learning it today. So the best example I know is, for instance, I'm a chess piece. I'm on a white square. If and only if I'm not on a black square. So if I'm not on a white square, I know automatically I'm on a black square, and if I'm not on a black square, I know automatically I'm on a white square. All right, so this is so that means that if all the elements A and B Ij are the same, then the matrices are the same. So this is equality. Yeah, assigned. How do I write assigned? Do I have spelling there? I think I have spelling. Ah, yeah, it's assigned with one S. Okay. Okay. So that's pretty self-explanatory. Transpose. You take you invert the rows and columns. Not to confuse with some other notion of complex conjugate that you use in quantum physics, I think, where you transpose the matrix and you flip the real part for imaginary part of the numbers. This is not that. So it's a very simple notion. So as we said, you just flip the rows and columns. So for instance, you have so if I have a 3x2 matrix with A, B, C, D, F and I take the transpose, then what I get is, oh no, it's not, that's not that at all. Yeah, I don't know if I can get it with this compute matrices transpose. Yeah, good. So you see that, so the what's in 1-1 stays in 1-1, what's in 2-2 stays in 2-2, but A2-1 becomes the matrix 1-2, and also the dimensions change. So here this is a 3x2 and it becomes a 2x3. All right. Yeah, that's so by the way, you may also see, so especially in maths, in more context or statistics, A then transpose, or sometimes they have some special thing like, do I have it here? I don't know if I can find it. Oh yeah, this, I think, or different other symbols. But so this all means transpose. So here we're going to use prime. Okay, so sorry about people who are familiar with another notation. So it may mess with your brain somehow, but yeah, we need one and we're just going to use one. So this is something that we see a lot in econometrics. So that's what we're going to use, all right? So I think they're all as good. I'm inclusive as a person. I like the diversity, but at some point we have to settle on one notation. So we're going to use that one. All right. So yeah, so I could tell you the general things. So if I have A prime, which equals, so I have A ij, then I take the transpose of this, then it gives me, oops, A ji simply for every I and every j. So this is a super compact way of expressing it. Oh yeah, I remember what I wanted to say. It's this. So column vector here is a vector of with, it's like a matrix with a single column. This is like a matrix with a single row. So there is a debate, maybe especially in computer science, whether a row matrix or a column, a row vector or column vector has dimension, say 3x1 or 3x0. I'm not going there. So it's sort of philosophical, but it sort of have implication into how you deal with it. Different computer programs express it in different ways. So if you use MATLAB, everything is a matrix. So maybe for those who haven't heard, MATLAB is a very neat program that allows you to do a bunch of scientific computations. Here, I'm just going to say you use the MATLAB definition. So yeah, this is the dimension is 3x1, 1x3. But know that some people say that you should just have 0 dimension. Yeah, without going into the too much detail. All right, so now I have been talking for a while. So A prime prime equals what? same. So A prime prime equals A prime prime. Yes, A prime prime equals A. Because if I flip once, I get this, but if I flip again, then I get back the original matrix I have. Yeah. Okay. Note. So this is, yeah, this is one. One thing I already said. Yeah. Just one thing I want to add about column vectors is by convention, vectors are column vectors. So they start their life this way. So, but sometimes you may express a vector in this fashion. So that's so in that case, you would write it this way to say, yeah, I know that my vector is a column vector, but if I want just to write a single in a sentence, then this messes up my line, line formatting, especially if it has like 10 variables in it. So it's going to create a huge white space on my page. So then I can see, yeah, I'm going to write it this way, but know that it starts by being a column vector. So this is why we write it this way. Okay. Where was I? Okay. Multiplication by a scalar. So if I have S that multiplies A, this is equal to, so I can rewrite A in this neat way. So S that multiplies the matrix A, Aij. And what is this equal to? Well, it's equal to a new matrix where S multiplies each element of the matrix. So for instance, if I have S that multiplies, let's see, A, B, C, D. So it's going to give me, oops. Yeah, this is better. SA, SB, SC, SD, right? So this makes sense. So in all of these rules that I'm going to do, they all come from the fact that matrices are used to express systems of equations. So here, this means that yeah, if I multiply all of the coefficients by a constant, then it's like if in my matrix here, which represents the coefficients, I multiply all the coefficients by a constant. So there's always this, I want it to be able to mean the same thing. So this means, sort of means if I multiply all the equations of my system of equation by some constant. Yeah. Okay, addition or subtraction. Subtraction or subtraction. Subtraction. Yeah, I shouldn't doubt myself. I write it well the first time and then I doubt and I change it. So that's a good lesson for the exam. Trust your feeling. If you do it once and it looks good, then and you read again your exam and you think, oh, maybe this is wrong, but yeah, oftentimes the first time was the first way of doing it was the right way. Okay, so now I'm going to have two matrices, and I'm going to indicate the dimensions, which will be M by N. So just by writing the matrices this way, then I get a very good feeling of what's going to happen. If I add both matrices, what should I get? Yes, exactly, Mr. Naftej, or it might be your first name, so Naftej. So I get AIB plus AIJ plus BIJ. So it makes total sense. And what you see is if I have, so I must have exactly the same dimensions. So I'm just going to give you an example with subtraction. So if I have, yeah, let's use that one. Minus then one with H. So is that going to compute it for me? Yeah. So that's what you get. So you just go element by element. And so you do the operation. So of course, if you have 3 rows here, you cannot just assume that there's nothing. You need, well, you just add a row of 0, but you need to have the same dimensions. So this would be A minus E, B minus F, C minus G, D minus H. So very important. Both matrices have same dimension. Oh, by the way, how long are we going? Are we like close to the end now, or 1 minute? All right. So what do I do? Yeah, I didn't have time to see all of what I could have seen, but it's too long to continue for sure. Yeah, so I think I'll stop here. I don't want to impede on your time. And yeah, or is there questions of what we're seeing? Yeah, I know that most of what we've seen is super descriptive and notational, but yeah, we have to start this way. Yes, next class is in person. Okay, so thanks a lot, everybody. I'll post some TA sessions for Friday, but I don't know, maybe I have enough things to make you do stuff. And then we continue on Thursday. Okay, so have a nice end of the day and tomorrow.